Hello, I'm David Brown. I'm the chair of the International Neural Network Society History Committee. We're carrying out a series of interviews with our founding fathers, our pioneers of the AI field. Today I'm talking with Professor George Lendaris. George G. Lendaris is Emeritus Professor of Systems Science and of Electrical and Computer Engineering, Portland State University in Portland, Oregon. He received the Bachelor of Science in 57, Master in 58, and Ph.D. in 1961 in Electrical Engineering from the University of California, Berkeley. After receiving his Ph.D., he joined the GM Defense Research Laboratories, where he did extensive work in control systems, neural networks, and pattern recognition. In 1969, he went into academia, first joining the Oregon Graduate Institute, where he was chair of the faculty, and 2 years later moved to Portland State University, where he became one of the founders and developers of their Systems Science Doctoral Program, where he served for 41 years, retiring in 2011. He expanded his academic and research activities into general system theory and practice, and later substantial effort into computational intelligence research based on neural networks. He served in a number of capacities at Portland State, including President of the Faculty Senate, Director of the Systems Science Graduate Program, and the Director of the Northwest Computational Intelligence Laboratory. He actively participated in the neural network professional arena as well, serving in a number of capacities, such as a member of the ADCOM of the IEEE Computational Intelligence Society, elevated to Fellow of IEEE in 1982 in recognition of his seminal work in pattern recognition, and then Life Fellow in 1997. And ultimately, in the Neural Network Society, a member of the Board of Governors, President of the INS, and Fellow of the INS, elected in 2004. His activity in neural network research began in the early 1960s, with focus the last 3 decades on modularized neural networks and reinforcement learning methods, focusing on application of adaptive, critic, and dynamic programming methods to online design of optimal controls for changing systems, culminating in developing his ideas of experience-based controls. Well, George, that's a very impressive bio. Now I like to get into asking you a few questions. Beginning, well, how did you get into the field?
How did I get into the field? It's fair to assume we're talking about neural networks field, and we'll go from there, right? Okay, I'll say that this is where initial conditions come into play. And so let's go back to my senior year in electrical engineering at UC Berkeley back in 56, 57, wherein, my coursework focused on control systems. In those days, the context was still on linear, time invariant systems. Turns out I did a senior project for one of my professors, Professor Otto Smith, that designed and experimented with a device whose output in time provided the mathematical equivalent of what we called a complex zero signal generator, and focused on using such a signal generator to identify the transfer function of a linear second-order system mathematically characterized by a complex pair of poles. Okay, this experiment went very well, and I wrote a paper describing it, for which I received the regional first prize for a student paper in the California district of what was then the AIEE, the American Institute of Electrical Engineers, which was one of the precursor societies for what later became the IEEE. Okay, I continued research along this line leading up to my dissertation entitled On the Identification and Adaptive Control of Sample Data Systems. and then a subsequent paper entitled On the Identification of Linear Systems that was published in the IEEE Transactions. Now, during my last years at Berkeley, here we're talking more about initial conditions. While I was writing my dissertation, Professor Lotfi Zadeh had arrived at UC and offered a new course related to learning automata. My dissertation work wasn't specifically along that line, but I sat in on that course. Okay, after receiving the Ph.D. in '61, my first job was at the General Motors Defense Research Laboratories in Goleta, California. Somehow, even though I had 11 job offers, those were heady days when we were graduating with PhDs in electrical engineering, I decided to take that one down in Santa Barbara. Now, the context there was that GM had decided to get into the space-related projects and set up this laboratory just outside of Santa Barbara. And all hands were on deck relative to achieving this stated goal of GM. But about a year into it, the lab director called a meeting of all of us technical staff and informed us that GM decided that they were too little too late for the lab's original objective of getting into the space program. And the director was given a 3-year budget to map out a new direction for the laboratory. And he invited all of us to team up and develop proposals and to pursue technical problems of our choosing. And he would serve as customer, if you will, and would evaluate all the submitted proposals and fund accordingly. Turns out the office mate I had been assigned to had an interest in learning automata, even though my dissertation had focused on the real-time identification and adaptive control of dynamical systems. The happenstance that I'm calling it of my having sat in on Professor Zadeh's course on adaptive automata turned out providing a rather different path, which led to my future work related to using the NN technology, the neural net technology, to implement real-time system identification. And simultaneously to implement associated adaptive control, all of which took several decades to materialize. Okay, another important ingredient here was how young the computer field was at the time in the early 1960s. And in particular, how limited we were related to data we could introduce while the system was running online. Now, as a context, my academic training was primarily related to the identification and control of linear systems, and later graduated along with the field into nonlinear systems. Now, as a budding controls engineer, I was used to characterizing dynamical systems of such systems via their frequency response characteristics, and even in that context with rather sparse properties of the frequency response itself. Now, one of the objectives given to us at the lab was to support the needs of other projects being pursued there. Now, one of these turned out being one of pattern recognition. All right, so simultaneous with this timing, I ran across and read a paper that explored the fact that in an optical system, the pattern that shows up at the focal plane and centered on the downstream optical axis of the principal lens, known as the Fraunhofer diffraction pattern, turns out being mathematically equivalent to a Fourier transform of the two-dimensional image being projected by that main lens. So there we were, representing a two-dimensional pattern via its three-dimensional frequency response. Okay, what was at that point left for me to figure out was an efficient way to represent such data. And again, remember the minimal status of computers in those days. So this led to the development of a way that employs the amount of light energy that passes through a prescribed shape two-dimensional window centered at the focal plane of the main lens. Now, we call these sampling windows. The shapes of the sampling windows were crafted, according to computational capabilities of the system and to the needs of the pattern recognition task. All right, to make this long story a little shorter, those ideas were expanded and developed for optical pattern recognition tasks. I spent 8 years there at the Defense Research Labs, and then finally moved on to higher education, which was my long-term objective in the first place. One of my professors had said, if you want to be a good engineering professor, you should spend about 10 years in industry. And so that was my proxy for spending time in industry, was at that research lab. So that turned out being 8 years when this opportunity came up to join a faculty up in Portland, Oregon. So this provided some real world, if you will, experience to take with me into academia. So in 1969, I moved into academia, where I spent then some 42 years. The first 10 of those years I devoted to co-develop the Systems Science Doctoral Program at PSU in Portland. And the latter 30 years, I participated in the evolution of a portion of the budding field we're calling neural networks. Now, as an aside, in about a decade, I was made a fellow of the IEEE in recognition of the diffraction pattern sampling approach I had invented for characterizing and identifying two-dimensional patterns. All right, so now as the years rolled on, the computational capabilities at our disposal kept increasing, and our focus became shifted to what we started out calling adaptive logic elements. And finally, as time went on, over several decades actually, multi-layer neural networks. My primary application focus of the neural networks was online identification and adaptive control of time-changing systems. So that one-liner, that one-line description, online identification and adaptive control of time-changing systems is what covered the latter two decades of my academic research.
So really then would you say that is actually the answer to my second question? What are your most significant accomplishments?
Well, let me get to that, but let me take a sidestep and mention a little related to our profession here, in addition to our ongoing technical work. A number of us, including yourself, got involved with the founding and development of what became known as the International Neural Net Society, the INNS. Now, regarding my personal involvement in such activities, in 1993, I was general chair of what essentially turned out being the first annual neural network conference to be, subsequently that got offered jointly with the IEEE Neural Net Society. Now, this was a conference held here in Portland in the summer of '93, which I chaired. Now, related to the INNS, I served on its board a number of years and participated in a number of its activities, including in the early 2000s, I served a 3-year role as president-elect, president, and past president, and I participated in a number of committees before and after my tenure as president. And near the end of my active involvement, I was elected a fellow of the INNS. Now, getting back to my neural network-related work during my last 2 decades at Portland State, based on funding that I had received from the National Science Foundation, primarily via Paul Werbos, I was able to set up what was called the Northwest Computational Intelligence Laboratory at PSU. The work at our laboratory focused on the use of neural networks for what I mentioned earlier about the online identification and adaptive control of time-changing systems. The result of our research are described in a number of publications in our field's professional journals. And so these fall roughly into 5 topic areas. These were the experience-based control and context discernment, so-called adaptive critic methods, the pre-structuring of neural nets based on structure and data. And and then another couple, bridging symbolic AI with neural net-based AI, And last but not least, application to online identification and adaptive control of time-changing systems. Okay, so then I retired from the university in 2011, and in the years since, I've been mostly reading into and focusing my attention on what physicists are learning about our physical universe based on ideas and a deeper understanding of quantum mechanics, but that's a different story. So now we can go on to your next question, which was what?
I think you covered a number of questions. My next question is, what are your most significant accomplishments?
Well, I like to characterize these in two main topic areas. The diffraction pattern sampling approach I invented for characterizing and identifying two-dimensional patterns that we talked about already a fair amount. And then the second category, the use of neural networks for the online identification and adaptive control of time-varying nonlinear dynamical systems. I keep repeating that because all of those were important, have been fundamental to the work my last 20 plus years at the university. Now, so I guess let me put it also the same thing, repeating it, I guess. I want to say that this category that I call the use of neural networks for online identification and adaptive control of time-varying nonlinear dynamical systems, that one-liner stands proxy for some 2 decades of work. And now a summary of the key elements of this work is provided in my 2009 paper, which is entitled Adaptive Dynamic Programming Approach to Experience-Based Systems Identification and Control. And this was published in Neural Nets Journal that year in 2009. And so that basically encapsulates that whole, well, two and a half or so decades worth of research. And I would direct any of the listeners who are interested to look up that paper. It was in the Neural Networks, the INNS's publication in 2009. Okay, that's where we're at.
And my next question, which I think you also have covered, what are you up to these days?
Well, okay, so I've been retired from academia now for some 12 years. And during that period, I've decided to rather substantially, let's say, switch gears. As such, I've set aside all my previous work related to neural networks, pattern recognition, controls, etc. And instead, I've taken up readings associated with quantum mechanics and related interpretations of how our physical universe works. And this, of course, entails a whole different kind of conversation, not necessarily appropriate here. So but the idea there is that I really switched on what I was doing before. I said behind me what I had done the previous 4 decades, and here we were in a whole new exploration.
Well, it certainly sounds like fun anyway.
It has been intellectually fun. Yes, that's a good one.
My next question is, what were the early days of INNS like?
Well, I suppose they were similar to any new fledgling society might face. They were exciting times, though, as decisions had to be made about almost every aspect of creating and running an organization, such as the INNS was intended to be. Though there were a number of fixed opinions here and there and about how to proceed, generally, my experience was one of congeniality and willingness to grow together. In my view, a key ingredient for the success INNS has enjoyed was the willingness by those involved to do what it took to provide a successful path for the INNS. Importantly, I'd say that the chemistry among role players seemed to have worked out extremely well over the years. And there are many great examples among the previous role players. Okay, I guess that says what were the early days of New York INS like.
Well, what do you see for the future of the societies here, in particular for INS? What sort of role should INS play moving into the future?
In the early days of AI, there was a perceived to be two distinct approaches to implement artificial intelligence, quote unquote, namely top down and bottom up. Now, due to what I would say was a fair amount of elitism among the proponents of the top down approach, the very term AI was related in people's minds to the top down approach. However, more recently, with higher and higher rates of success among the bottom-up approach, which neural networks represents, the term AI is having to change its meaning, in my view, in order to reflect the reality of what's occurring technologically in the field. So we in the NN field, the neural networks field, could serve this end by helping to build mental model bridges, let's say, among proponents of what used to be called bottom-up versus what was called top-down. In the end, it's likely to be best for practitioners to keep in mind the facts demonstrated by humans and animals regarding the wholeness of intelligence. And so we should participate in expanding that whole idea and feeding it, nurturing it.
I think you're always staying one step ahead of me. You're getting into what are people doing right or wrong in AI research now?
Yeah, well, I guess it's a little presumptuous to declare certain modes of operation while pursuing what we're calling AI as right versus wrong. But I do suggest, however, that it's useful to keep in mind the history of the research and application in this arena over the past number of decades. In particular, the presumptiveness that we human researchers have demonstrated relative to the top-down versus bottom-up. There seems to be need and usefulness for both approaches rather than one being superior to the other. So right, wrong, well, there are different approaches, and I think that we need them both.
Okay, finally, George, what advice would you give for a researcher just starting out in the field?
Well, as I mentioned at the beginning of our discussion here, for me, it was a confluence of initial conditions, quote unquote, that took place over a period of about 3 years or so. That got me into the path that I ended up pursuing for the following close to 50 years. According to that model, I would suggest to the budding researcher to take a, let's call it a high-level look at what has gone on in his or her developmental paths, which led to the then present point in their career, as this provides information about the person's research inclinations and potential contributions. And key advice is to make sure to notice what evokes your intellectual pleasures as new ideas have emerged. And also be open to the fact that what's to be worked on next, say 40, 50 years, will morph rather dramatically, I'm going to suggest, as the years roll on. And it'll be important to keep abreast of new ideas and tools and that may become available at each step of that timeline. And most of all, enjoy the ride.
Okay. Thank you very much, Professor Lendaris. Very much enjoyed talking to you. George, it's good to see you. You're looking well, and hope everything continues to work out well for you. Thank you very much.